Hey everyone. So in this video, I like to talk about sine and cosine. So in your previous classes, you discussed functions and many big picture qualities of functions. Some functions you looked at were polynomials, rationals, rational functions, exponential, and logarithmic functions. And so some things you looked at were, how to determine outputs from particular inputs. Maybe for some functions, like let's say f of x is equal to x squared minus 9, this was pretty clear, right? If I plug in some value for x, well, I square it, take away 9, and I know my output. But for some other functions, let's say like logarithms, you really had to understand what that function meant to compute the outputs. So for example, let's say I have g of x is equal to log base 2 of x. Right? If I plug in, let's say 8 for this function, right? This is asking us to compute. This is saying, what power of 2 gives us this input 8. And in this case, based on our familiarity with powers of 2, we know that 2 raised to the power 3 gives us 8, and so the result of this is 3. The output when we input 8 is 3. But if I plug in something like 10, we know the idea behind what this output's going to be, and we have some rough sense, but we don't have a way of calculating this without maybe a calculator. This is still asking what power of 2 gives us 10, and it's going to be something a little bit more than 3 if 2 to the power 3 gives us 8. And then, with the calculator, we'd be able to see that this is roughly 3.3219. Okay, so, we talked about how to compute outputs from inputs. You talk about domain and range, graphs, inverses, and many other different topics for functions. And so, in this class, we're going to do the same thing, and we're going to talk about sort of apply these ideas to 6 new functions that we're going to call trigonometric functions. And there's sort of 2 functions that I want to give a little bit of extra attention to in the beginning. Really, all of the 6 functions, all of the remaining 6, the remaining of the 6 functions are really described in terms of these 2 functions, sine and cosine. So these are the things I want to focus on a little bit more and talk about in this video. And so, like logarithms, there are many inputs that we can't really determine the output of directly without a calculator, without any extra information. But I want to define what the inputs and outputs mean, and some nice examples of some outputs we can determine from these functions. And so these 2 functions, they're really going to form the foundation of this class alongside the topic of radians. And so really this is something I want you to understand very well, and not having a shaky understanding of this is going to make the rest of the class significantly harder. So this is something that you want to pay extra attention to or work a little extra hard to make sense of. And so let's go ahead and define these 2 functions, sine and cosine. And I want to do this in terms of circles. So let's say I've got a circle here on the left. It's a circle of radius r. And maybe let me take a look at one point on this circle. It's got an x-coordinate and a y-coordinate. And so here it's a circle of radius r. And we've been talking about angles. Let me attach an angle to this point too, right? So here, really, I can kind of think of this point as being at sort of the end of this angle here, an angle of theta. Again, this point is on the unit circle, And one way we can sort of make sense of these coordinates and visualize them in a slightly different way is, well, this y-coordinate is telling us how high this point is away from the x-axis, right? It's that y-coordinate is really describing that distance there. And the x-coordinate, we can kind of think of it the same way. We can sort of think of it as this measurement here, dashed blue line telling us how far away this point is from the y-axis. And so there's kind of a right triangle floating around here. And one thing that I want to point out in this picture is that there are some ratios here that actually don't change even if we change the size the size of the circle. All right, so let's say I've got the same angle traced out in a larger circle. So maybe I've got this angle here. Maybe it looks like so. It's the same angle theta, the same angle. Different radius. Maybe I'll call it R2 just to really emphasize. It's a radius, but it's different than our previous example. We've also got a point at the end of this radius on our circle. Maybe again, let me give it a different name. Let me call this x2 and y2. Right, so again, there's sort of a similar picture here. There's y2 kind of measures the distance this point is away from the x-axis. This is that measurement y2, and x2 measures the distance that point is away from the y-axis. Right, so this measurement is x2. And again, there's sort of a right triangle floating around in this picture. And so I was saying there's some ratios in here that are the same regardless of the size of this circle. And these are the ratios x over r in this first circle. If we take this x coordinate and divide it by the radius of the circle, that actually ends up being the same as the ratio of x2 over r2 in this second circle, right? So this x coordinate divided by the radius in this second circle. Right, so these ratios, they're the same, and they really just depend on this angle theta. And so similarly, we can also examine this ratio y over r. It's the ratio of the sort of height of this point divided by the radius. That ends up being the same as, even in this larger circle, as long as we're talking about the same angle here, y2 over r2. And so the height of the second point divided by the radius gives us the same ratio. And so we call these ratios cosine of theta and sine of theta. Right, so this first one, this is cosine of theta. It really just depends on the angle, not so much the size of these measurements, the size of these side lengths and the radius. And so we can sort of think of it as a function of the angle. And similarly, we can think of the second ratio as again, a function of the angle. And this is what we call sine of theta. For any circle, we think of cosine of theta as the x-coordinate of the point on the circle corresponding to the angle of theta divided by the radius of the circle. And then for sine of theta, this is taking the ratio of the y-coordinate on the circle corresponding to that angle divided by the radius. Right, so here, again, I just want to emphasize that these are really determined by the angle, by theta. And the fact that these ratios are the same here, these equality signs, that's really a property of similar triangles. So to get a sense of how to evaluate sine and cosine, I'd like to recall what the side lengths are of a 30, 60, 90 triangle. So we took a look at one of these examples earlier in the class. We said if we have a 30, 60, 90 triangle, the example we looked at had a hypotenuse of 2. By sort of looking at this in the context of an equilateral triangle, we're able to recognize that the side opposite the 30-degree angle, well, that was half of 2, that was 1. And the side opposite the 60-degree angle, the larger of those two angles, that was the square root of 3. And that in general, if I have some side length s here for the hypotenuse, by playing the same game, we can recognize that this shorter side length was just half of that hypotenuse, and this larger leg length, well, that was the square root of 3 over 2 times that hypotenuse. Right, and so maybe another concrete example is if I have a hypotenuse of 8 for this 30, 60, 90 triangle, well then the shorter leg length is 4, half of that side length of 8, and the larger leg length, well, it's 8 times the square root of 3 over 2, it's 4 square root 3. And then, oftentimes in this class we're going to be looking at triangles with the hypotenuse of 1, right triangles with the hypotenuse of 1, and so we can kind of do the same thing and see that we'll get a short leg length of 1/2, and well, the square root of 3 over 2 times 1 is just the square root of 3 over 2. That'll be the size of our larger leg length. Okay, so let's go ahead and try to evaluate cosine and sine of 30 degrees. And let's do this twice, one for a circle of radius 2 and one for a circle of radius 8, just to showcase that these radii, their differing measurement isn't going to change the value of cosine or sine. So in this first picture, we're dealing with a circle of radius 2. And we want to sort of explore cosine and sine of a 30-degree angle. So here, if I've got a 30-degree angle, maybe let me just roughly sketch it. I think that might be an okay place for 30 degrees. So that's 30 degrees. There's a point on this circle at the end of that 30 degrees. Right, it's got an x-coordinate and a y-coordinate. But because this is 30 degrees, we can kind of picture that there's a triangle floating around in this picture. This y-coordinate, whatever it is, it's this measurement here, the height of that point above the x-axis, and then the x-coordinate is sort of the distance that point is away from the y-axis. Right, so there's this right triangle floating around where that green side is this y distance, the value of this y-coordinate, and this blue side is the value of this x-coordinate. And because this is a circle of radius 2, and we can sort of see this triangle in this picture has an angle of 30, 90, well that's telling us this remaining side, or this remaining angle is 60 degrees. And so this is a 30, 60, 90 triangle with the shorter leg length being half the hypotenuse, so 1, and the larger leg length being the square root of 3 over 2 times hypotenuse, in other words, the square root of 3. Right, so that's this x-coordinate, and this y-coordinate's 1. And so cosine of our angle, cosine of 30 degrees, well, it's this ratio, the x-coordinate divided by the radius of this circle. And so the x-coordinate is the square root of 3. The radius of this circle is 2. And we can't simplify this any further, so cosine of 30 degrees is the square root of 3 over 2 based on this picture here. And then we can do the same thing for sine of 30 degrees now that we know the coordinates. Right, sine of 30 degrees, that's the y-coordinate associated to this 30-degree angle on the unit circle, or on this circle, and we're going to divide it by the radius of the circle. So we have 1 as the y-coordinate divided by 2 is the radius. Okay, well, if we do the same thing for this larger circle, maybe a 30-degree angle would look something like this. Right, so there's a point on the circle corresponding to 30 degrees. It's got an x-coordinate and a y-coordinate. And the y-coordinate is this measurement here. The x-coordinate is this measurement here. And there's a triangle, a 30, 60, 90 triangle, sort of alongside this picture. And so this radius, this measurement here is 8, right, the measure of this hypotenuse. You know that the short side is half of that, it's 4. And the larger leg length, well, that's the square root of 3 over 2 times 8. And we saw earlier that was just 4 square root 3. And so 4 square root 3, I guess I didn't leave myself enough space here, 4 square root 3. And so if we compute these ratios, right, cosine of 30 degrees, based on this picture is going to be, well, it's going to be the x-coordinate of this point corresponding to 30 degrees on the circle divided by the radius of this circle. And that's going to give us 4 square root 3 over 8. This is square root of 3 over 2. And then sine of 30 degrees is going to give us the y-coordinate of the point on this circle corresponding to 30 degrees divided by the radius of the circle. And so here we get, well, what is that? That's 4 over 8. That's 1/2. Right, so here, regardless of the size of the circle, regardless of the radius, we ended up with the same ratios. Right? And so really this is a property of similar triangles. And really, one thing I want to point out here is that knowing the coordinates really came from understanding the side lengths of that special right triangle, that 30, 60, 90 triangle, and sort of fitting it into the picture. Okay, and we used degrees here, but typically for the rest of this class we're going to refer to angles in radians. And so what can we say here? What's the analogous statement we can make in terms of radians? Well, recall that pi radians corresponds to 180 degrees. And so 30 degrees here, that's taking our 180 and dividing it up into 6 parts, right? So if we divided the right side by 6 to get 30, we'll divide in the left side by 6 would give us the corresponding radian measure, pi over 6. So the analogous statement we can make in radians is that cosine of pi over 6 is equal to the square root of 3 over 2. And sine of pi over 6, right? Sine of 30 degrees is equal to 1/2. And so one thing I like to point out is, in our previous example, the size of the circle didn't influence the result of these ratios. And so oftentimes we're going to really consider things in terms of the unit circle. X squared plus y squared is equal to 1. Right? So a circle of radius 1, centered at the origin. And so, that kind of makes some of these computations nicer, right? If I have cosine of theta is equal to x over r, if we're sort of thinking about things in terms of the unit circle, that value of r is just 1. And so I'll talk about this again in just a moment, but here let's go and continue. Let's do a few more examples. So, in the same vein of recalling the side lengths of a 30, 60, 90 triangle, another right triangle, special right triangle that we emphasized was this 45, 45, 90 triangle. And so here, when we took a look at a 45, 45, 90 triangle, the first one we looked at had leg lengths of 1. Right? They're isosceles triangles. They have the same angles here and the same side lengths here. We notice that the hypotenuse, if we do the Pythagorean theorem, perform the Pythagorean theorem, we get the square root of 2. And one thing you can notice is that really the leg lengths, the relationship to the hypotenuse is that you take the hypotenuse, and if you divide by the square root of 2, you get the leg length, right? So if I take the square root of 2, I divide it by the square root of 2, I get my leg length of 1. And so if I have some general side length S for my 45, 45, 90 triangle, and I want my side length, my leg length, what I would do is I would compute S divided by the square root of 2. And now, unfortunately, we aren't going to typically see our leg lengths in this particular way when it comes to 45, 45, 90 triangles. Oftentimes, we will rationalize the denominator. So that just means getting the square root out of the denominator. We can do that by multiplying by the square root of 2 over the square root of 2 to the numerator and denominator. And that's just a fancier way of multiplying by 1. And so we end up with S times the square root of 2. And then this square root of 2 multiplied by the square root of 2, that's just 2 itself. And so we can sort of think of this as S times the square root of 2 over 2 as a whole. S times the square root of 2 over 2. That's really what this side length is. It's just another way of saying S divided by the square root of 2. And so to give a concrete example, and again, let's do this with where we have a right triangle with a hypotenuse of 1. We have, let's say 1 here. The side length, the leg length, has then a measurement of 1 times the square root of 2 over 2. So the square root of 2 over 2, the square root of 2 over 2. So let's go ahead and use that last idea to determine sine of 5 pi over 4 and cosine of 5 pi over 4. And if you're feeling up for it, I definitely encourage you to pause the video and try out these examples yourself first. Okay, but doing this together, how can we begin this problem? Well, first thing we need to do is make sense of what 5 pi over 4 really is. What angle does that represent? And so there's a few ways to interpret what 5 pi over 4 is. You can kind of think of this as 4 sets of pi over 4 plus pi over 4. And so that's one way to think about it, where this is just pi, right? So this is just pi plus pi over 4. And so pi over 4, actually maybe let me start with pi. This is 180 degrees. Pi is 180 degrees. Right, so we know that we're going at least 180 degrees here. And then pi over 4, this is an extra 45 degrees, right? If pi is 180, then pi over 4 is 180 divided by 4. And that's 45 degrees. So here we're going an extra 45 degrees, right? Half, or how should I say this? A quarter of a half rotation. And so this ends up being this angle here. Okay, where this is 45 degrees on top of the 180 degrees. Right, so there's this point on the unit circle corresponding to that angle of 5 pi over 4, which is 225 degrees, where we can, like we see above, we can sort of imagine it as 180 degrees and then a further 45 degrees. So right, there's an x-coordinate and a y-coordinate to this point. So the y-coordinate is this measurement here, that measurement away from the x-axis, and the x-coordinate is this measurement here. Right, so there's a right triangle floating around this picture, and it's a 45, 45, 90 triangle, where we have a radius. Here, we said that it doesn't matter what radius of a circle we use. So here, maybe for simplicity, let's think of a circle with a radius 1, right? The unit circle. And in this case, based on our previous example, we saw that if we have a right triangle with a hypotenuse of 1, a 45, 45, 90 triangle with a hypotenuse of 1, the side lengths are the square root of 2 over 2 and the square root of 2 over 2. And so in this picture, if we have this hypotenuse of 1 for this 45, 45, 90 triangle, these side lengths are the square root of 2 over 2 and the square root of 2 over 2. But one extra thing we have to be careful about is that, we're not just looking at this triangle and the side lengths. We're looking at this point on the unit circle. This is a point, it's an x-coordinate and a y-coordinate, and it has some sign to it. It's positive or negative for each coordinate. And so notice that because this triangle sort of positioned to the left of this x-axis, it's really negative the square root of 2 over 2 is that x-coordinate measurement, right? This is negative square root of 2 over 2. And then similarly, because this point is below the y-axis, really this coordinate, although the side length is the square root of 2 over 2, the coordinate is negative the square root of 2 over 2. Right? Because again, we're talking about a coordinate, a point on the plane. And so because it's below the y-axis, it's got a negative y value. And so that distance there, that's the square root of 2 over 2, we're really recognizing that as a negative measurement. Similarly, this x value here. And so sine of 5 pi over 4, right? This is the y-coordinate of the point on the circle corresponding to our given angle 5 pi over 4, and divided by the radius. Well, in this case, we're dealing with the unit circle. The radius is 1. The y-coordinate is negative square root of 2 over 2. So dividing anything by 1 is just negative square root of 2 over 2. Just the numerator, right? And so cosine of 5 pi over 4, right? It's the x-coordinate of the point on the unit circle divided by the radius of that circle. And in this case, the radius is 1 again, and we also have our x-coordinate is, again, negative square root of 2 over 2. And so we just end up with negative square root of 2 over 2. Okay, and so I want to go back to this idea of using the unit circle here, so we can kind of notice that what we ended up here with sine of 5 pi over 4 and cosine of 5 pi over 4 were exactly these values. Right? And because sine and cosine take the y-coordinate and the x-coordinate and divide it by the radius, when we're dealing with the unit circle, and the radius is just 1, and so in general for the unit circle, if I have, some point here corresponding to an angle of theta, and cosine is x over r, well, this is just x over 1, which is just x in this case, right? And sine of theta is y over r, it's just y over 1, which is just y in this case, only when we're dealing with this unit circle. Right? And so what we're saying here is that on the unit circle, the x-coordinate is the same as cosine of theta. And the y-coordinate is the same as sine of theta. And so really when we're on the unit circle, cosine of theta is the x-coordinate, sine of theta is the y-coordinate. Really the points on the unit circle tell us cosine and sine of that angle. Here, let's just wrap this up with 3 last examples. So if you're feeling up for this, again, let me encourage you to pause the video and try these examples out. But otherwise, we can do these together. So this first example is to compute sine of 2 pi over 3 and cosine of 2 pi over 3. And so first things first, let's determine what 2 pi over 3 is. Right, so 2 pi over 3, right, this is 2 sets of pi over 3, which is 2 times, well, pi over 3 is the same as 60 degrees, right? If pi is 180 degrees, dividing that up into 3 parts gives us 60 degrees, and then 2 sets of that is 120 degrees. Right, so a little bit more, 30 degrees more than 90, or 2/3 of the way around towards pi, right? If pi radians is here. And so I think this is about right for our angle of 2 pi over 3. And so we're looking at this point here. And there's sort of, again, there's a triangle in this picture where its y coordinate is this measurement here and its x coordinate is this measurement here. And so, you know, if 2 pi over 3 is 120 degrees, what we're really saying is that the rest of this way to pi is 60 degrees, right? So this is a 30, 60, 90 triangle, right? If that's 60 degrees and this is 90 degrees, so the remaining angle in this picture is 30 degrees. And if we're dealing with the unit circle here, then that's telling us that the short side is half of that radius, 1. So it's half of 1, it's 1/2. And that larger leg length, that's the square root of 3 over 2 times 1. So just the square root of 3 over 2. And then I got to pay attention to my whether or not these side lengths correspond to positive or negative values, right? This 1/2, you know, that's an x-coordinate. It's on the left side of this y-axis. So that's a negative value. This is negative 1/2. And then because the square root of 3 over 2 is being measured above the y-axis, above the x-axis, then we're dealing with a positive measurement, right? This point here, it's above the y-axis, its y value is positive, so that square root of 3 over 2, the y value is a positive measurement. Whereas the x value of 1/2, that's a negative measurement because it's you know, on the negative side of the x-axis. Okay, and so again, you know, we're dealing with the unit circle here. These correspond to our cosine and sine values. But maybe just to rewrite this out, right? Sine of 2 pi over 3, this is equal to the y value of the point on the unit circle corresponding to an angle of 2 pi over 3 divided by the radius of our circle. And if we're dealing with the unit circle, then here we just have an r value of 1, a y value of the square root of 3 over 2, and so dividing that by 1 is just still the square root of 3 over 2, just the y value itself. And then cosine of 2 pi over 3, this is the x value of the point divided by r, so this is negative 1/2 divided by 1, or negative 1/2 at the end of the day. Okay, so we've got 2 more examples here, cosine of pi and sine of pi. So here if I have another unit circle, then pi radians is telling me we're going halfway around this circle. And we're dealing with this angle here. And now if this is a circle of radius 1, then what is this point? This point is the point -1, 0. And we said that cosine of pi, well, this is the x-coordinate of that point on the unit circle corresponding to that angle of pi divided by the radius. The radius is just 1. The x-coordinate is -1. We get -1 at the end of the day. It's that same x-coordinate here for that unit circle. And then sine of pi, well, this is y over r, which is, well, it's 0 divided by 1. It's just 0, right? 0 divided by any number. If I split up 0 any number of ways, we still get 0 out. And so there's no triangle in this picture, but the point is rather nice. We can actually see it pretty directly what cosine and sine of these angles, or this angle, ought to be. And the last example, again, if we have the unit circle, if pi is 180 degrees, then pi over 2 is half of that, 90 degrees. So pi over 2 corresponds to this angle here. And if this is the unit circle, again, we're dealing with the point 0, 1, right? An x-coordinate of 0, a y-coordinate of 1. And because this is a unit circle, cosine is just the x value. Right, we saw that, in cosine it's the ratio of the x-coordinate divided by the radius, but the radius is just 1 here. So here we have cosine of pi over 2 is just the x-coordinate 0. And sine of pi over 2 is just the y-coordinate 1. And again, we don't have a triangle in this picture, but that's okay because we can still do this ratio, do this division of x over r and y over r. Okay, so those are many of the unit circle, not many of the unit circle, many of the angles I want you to be able to evaluate sine and cosine at. There are quite a few others, but I think that really showcases how you would go about computing them. Really, this is the full circle of values I want you to be able to readily compute. This looks quite intimidating. There's a lot here. What I want to encourage you or discourage you from doing is memorizing all of this. Really, the right idea is to sort of take the approach that we took today, is sort of looking at each angle and seeing what special right triangle can I fit in there and how can I fit it in. Right? For example, our first example we did was recognizing this 30, 60, 90 triangle fits here for this angle of 30. And we were able to use that to compute that the x value would be the square root of 3 over 2 and the y value on this unit circle would be 1/2. Right? So that's just knowing this special right triangle tells us this x and y value for this point on the unit circle, but it also tells us all the values corresponding to angle multiples of 30 degrees, as well as angle multiples of 60 degrees. And then we did the same thing for this 45 degrees, but we did that here for this example of 5 pi over 4. Right, so we were able to see that there's a 45 degree angle here, a 45 degree angle here, and we got that the coordinates were negative the square root of 2 over 2, negative the square root of 2 over 2. But really what this boiled down to doing was making sense of this 45, 45, 90 triangle. And so again, the main idea is get comfortable with these triangles, recognize how you can fit them in, and pay attention to what the signs of each coordinate should be based on where you're looking at in your coordinate plane.